It is the 5th of September. Where did summer go? 2019. So we had talked yesterday, we had started to talk a little bit about mixtures. Talked about the difference between heterogeneous and homogeneous mixtures. These are things that can be physically separated. We're going to do the other half of this chart today, which is the pure substances, and then we're going to dip back to mixtures. So if we have a substance, if we have something in front of us that cannot be separated physically, it has to be a pure substance, and there are two categories of pure substance. One are compounds, and these can be broken apart using ordinary chemical means. We can do that in the lab here. Maybe not all of them, but most of them. And some of them, under no circumstances, can be broken apart. Not by the means we've got. You'll need an atom smasher to break some of these apart. Or a newly formed universe, that would work too.
Or you just create like a couple of...
Do you need this for another moment? So the nice thing about pure substances is that their composition is fixed. Their composition is fixed. They are not mixtures. Every sample of a pure substance is going to have the same properties, the same characteristics. Doesn't matter if I'm talking about this, well, that's adulterated, or if I am talking, nope. Nope. Sodium chloride forms beautiful crystals. They actually have a different fracture pattern than quartz. There's a big salt mine a couple miles down under Lake Erie near Geneva, and they used to do tours of it for schools. They don't anymore. But while they still did, I got to go down there, and the walls are made of salt. They warn you, don't lick the walls. I was tempted. And we were allowed, as we were all science ed students, we were allowed to take samples. So we were allowed to bring backpacks back, and I've got some really nice chunks of salt, one of which is missing right now. This has got the same chemical composition as this does. Apparently the reagent grade sodium chloride that was up in the chemical supply here has gone downstairs. That has the same chemical composition. Same thing as regards our water. Whoops. This jug of distilled water has got the same composition as water from any place else on the planet, as long as it's distilled. We'll talk about impurities in a little bit. 1 oxygen, 2 hydrogens, no matter where you get it from. Glacier in the Arctic. Pond at your neighbor's farm. There's probably more cow poop in the pond at your neighbor's farm. The water itself has got the same composition. Oh, here's one. What is it? Aluminum, yeah. Nice metal that we kind of take for granted. Characteristic of metals, it can be pounded into thin sheets, such as this very thin foil. Samples of aluminum from any place across the planet are going to have the very same properties, the very same composition. This water and water from a glacier and water from any other location is going to boil at, don't you dare give me Fahrenheit. They think in Fahrenheit. You don't, I know. You come from some place where you handle units of measurement rationally. 100? Yes, 100. It's going to freeze at 0. This salt, this will become important to you. This salt, would liquefy, would melt, not at 0, but I forget, I always have to look it up. It's somewhere around like 3,000 Celsius. It's crazy high. Really hard to melt salt. You can do it, but not here. Doesn't matter where you get your salt. The characteristics will be the same. Now, not so. Mixtures well, even if their composition is uniform, even if they're homogeneous, they vary tremendously. And tomorrow you're going to get handed a mixture, which you will be asked to physically separate. So I wanted to talk a little bit about physical separations. We're used to looking at chemicals and thinking about their characteristics: melting point, boiling point, solubility, reactivity. But since we're talking about physical separations, we have to think about physical characteristics. Those can include things like color and shape. If you're picking chocolate chips out of the chocolate chip cookie batter, you're doing that based on a physical difference in color and shape. The manual separation. So the difference that manual separation relies on is appearance. If they look identical, you can't separate them manually. Give me a bowl of salt and sand, and I'm going to have a really hard time manually separating those because the grains will look quite similar to me. But physical separation is always based on difference. We can do magnetic difference, and we can then do, we'll get to that in a second, we can then do magnetic separation. Did you guys do iron filings and sand with Mr. Voorhees? Ignore that for right now. So you did the iron filings and sand. You can do iron filings and salt. And you separate the iron from the other material based on its magnetic attraction. That only works if there's a difference in their magnetism. You can separate things by filtration, which you've done. But there has to be a difference in their solubilities. So in the lab that you did, which one was soluble?
Salt.
Yeah, sodium chloride is soluble. Sand, not so much. If silicon dioxide was in fact soluble, beach vacations would take on a whole different dimension that I can't even begin to fathom. Wouldn't work. So silicon dioxide is insoluble. Salt is soluble. Therefore, we can separate them using filtration. We can dissolve one, and it will pass through the filter. Could we do sugar and salt that way? Anybody here ever made Kool-Aid? Okay. If you have not made Kool-Aid, you have homework. You think I'm kidding? That's cute. I'm not kidding. You should go home and make yourself some Kool-Aid. Is the sugar soluble? Yeah. Remarkably so. If not, you would have gritty Kool-Aid. You can't separate two things that have identical solubility using that solvent. Now, you could, if there is a difference in the point at which two things vaporize, go from a solid to a liquid or a liquid to a vapor, you can exploit that difference. Anybody here ever burn sugar in the bottom of the oven? Doesn't it smell delightful? Have you had cotton candy? Okay. I was going to say, you might not have, but okay, you have. Good. I don't know how widespread cotton candy is across the globe. Cotton candy is sugar that has been melted and spun, hardening into threads as it cools. Sugar melts at a temperature that you can achieve here in the lab. You can melt sugar over a candle flame. What did I say salt's melting point was? You don't have to remember. Yeah, you don't even have to remember a number. Just big. Huge. You're not going to melt it here in the lab. You're not going to melt it with a candle. You're not going to melt it with a blowtorch in your garage. Please don't try that. He was doing some interesting stuff in his garage, and he didn't burn it down while I had him in school. So, if you've got sugar and salt, we said you can't separate them based on filtration. Are they different on any of these characteristics? They don't look different. Is one of them magnetic? No, neither of them are magnetic. You can't separate them based on a difference in their magnetic attractiveness. You can't separate them based on a difference in solubility. Could you separate them by heating? Yeah. Would it be pretty? No, it would not. It would not be pretty at all. So let's do a little thought experiment. So this is similar to the form that you saw on the flow chart that you have with your lab. And I always screw this up. Do I? Pardon? Oh, 6. So it's not a correct formula. That's actually glucose. And I'm really talking table sugar, but I'm shorthanding. So let's say you got a pile of glucose. You could. So for our purposes on this flow chart, we'll say that substances are in boxes and actions are in ovals or circles or something. So we know that these two things have a different melting point and a different point at which they would vaporize. So let's actually, oh, I know how I lost the video. I know what I did. Let's actually look up the heat of vaporization for glucose. Are you thinking that there would be a separation here? Yeah, I think you're right. So what state would the sodium chloride be in afterwards? Oops, there's the answer. It'd be a solid. What state would the glucose be in? Again, do not yell it out. Jot something down and see if you agree with my assessment here. Oops. You use the difference in boiling point to do a physical separation because these two things can be separated that way. Now let me ask you this. If you ran this in a lab, heck, you don't, please don't, but you could do this on your stove at home. Please don't, because you will have that cloud of glucose vapor coating the kitchen walls, and you'll be on for the scrubbing, I'm sure, I would hope. Unless you tell them I did it, and then they might call me. I want no part of that. So you could do this on a burner on a home stove. 150 degrees Celsius is nothing. 160 is nothing. You can do that at home. You can heat it that high. If you're just doing this at home on your stove, are you capturing the glucose? At the end, will you have a pile of glucose and a pile of salt? No. No, it'll be all over the walls. The glucose vapor will be everywhere, a fine film of crunchiness. You haven't captured it. If you needed to capture it, this is not your method. Could you figure out how much glucose you had in your original mixture? Sure. How much mass did you lose? That's easy. But capturing it would take a little bit more sophisticated equipment, a little bit more of a setup than, the best pan in the house that you're going to burn the behoozes out of. Well, what if we're looking at something with a solubility difference? Other forms of ethanol will kill you if you consume them, like methanol, isopropyl alcohols. Those will all kill you. Ethanol won't kill you. It'll just get you drunk. So if I have two substances, and that is SOL, solubility. Sorry for the terrible handwriting. Solubility, my standard abbreviation. I didn't really improve that. If the answer to are these substances soluble in water is yes for both, can you separate them using water and filtration? Nope. Put them in water, stir it up, you got them both in solution. Now, a little down the road, we'll talk about solutions, we'll talk about solvents, but here the water and the ethanol are our solvents. That is what's doing the dissolving. Well, what if the answer to solubility in ethanol is yes and no? Can we separate these two things using filtration? Yeah, but we can't do it with water. So we can then take the same methodology and make a flow chart, A and B. what substance, I'm going to shrink my little properties table here. What substance would you have to dissolve them both in?
Ethanol.
Ethanol. Yeah. Get yourself a big old jug of ethanol. And the procedural step would be dissolve in, ethanol. Yeah, come up here after school. Okay. So dissolve in ethanol, and I'm missing one step of that because just dissolving them in ethanol is not enough. Then what do you have to do? You did this with your salt and sand. Yeah? What'd you put it through? A filter. So dissolve in ethanol and filter. What are you going to end up with?
A and B.
Okay, so let's address that. So let's say this is our filter. What, do not yell it out, talk to one another, what will be in the filter? Talk to one another. Think back to your salt and sand if you're struggling with that. A little bit of B? Yeah. Now, let me ask you this. When you had your sand in the filter paper, was it dry or was there water on that sand? Was the sand in your filter wet? Yeah. So will it really just be B in the filter? No. There would be B and some ethanol. Well, I need to reposition this a little bit more. What's going to be in the beaker? We call it the filtrate. What's going to be in the beaker? What dissolved in the ethanol? A. And is the A alone? No, it's dissolved in ethanol. You just said it. So have you separated A and B here? Yes. Do you have A and B by themselves yet? No. There's one step left. Now, fortunately, ethanol evaporates at a lower temperature than water. This is pretty easy. What step were you taking to separate the salt from the water in the lab? Talk to one another. Mutter at your tables. You were heating it. You were getting the water to vaporize. You were evaporating the water. You were actually boiling it. You were getting molecules to come out of the water column and go to the gaseous phase. And had we gone all the way to the conclusion, you would have had a crusty mess of salt in your evaporating dish. So this is, the filter is just a little damp with ethanol. We can just say, dry that. Then we get B. And we get ethanol I was going to ask you that. We get ethanol, but what phase is it in? It's a vapor now. It's all over the room now. That's okay. If we take the A that is dissolved in ethanol, and if we know the boiling point of ethanol, which I don't remember off the top of my head, but I'm going to say it's in the order, it's somewhere around 90 Celsius, 85 to 90 Celsius. We'll say it's 90. How's that? I could be wrong, but I'm close. So what if we heat this whole mixture to 91 degrees Celsius? What do we get? We get A. And we get, and I'm going to save myself the hassle, I'm just going to copy my little box right here that says ethanol vapor, because that's exactly what we're going to get. We're boiling off the ethanol. We're going to have ethanol vapor. Now, how many of you tried the flow chart in the physical separations lab last night? Okay. What I'm going to tell you is that everybody who looks at that the first time without any background completely fouls it up completely, and that's fine. I wanted you to just have your head into what a flow chart looks like. It's okay if it's all completely wrong. Based on our conversation here now, I think you'll do better when you look at it a second time. And I'm going to link, while you're taking your lab quiz, crud. Well, I think your lab quiz is tomorrow. I apologize. It's one more night to look over your safety stuff. So you'll have that when you walk in tomorrow, and then we'll go straight into the physical separations lab. You'll be able to get part 1 done, and the next parts we'll probably do on Monday. So I'm going to post the link to Chemical Handbook right now. If you want, you can also look in the back of your book. There's a nice handbook there. I'm not sure if they have this particular information or not, but you can check it, and I'll post the link I've used in the past. Questions, comments, concerns?